Dear students, after studying this module, you shall be able to know the importance of saturated heterocyclic compounds, design the synthesis of pyrrolidine and their derivatives, understand the retroanalysis and synthesis of pyrolysidine, design the synthesis of Esridines and Oxidanes, design the synthesis of oxazole and oxetane derivatives. Heterocycles are the cyclic compounds that contain, apart from the carbon atoms, one or more heteroatoms like oxygen, nitrogen and sulfur. Presence of heteroatom makes the ring easy to make by ring closing reaction or easy to break by ring opening reactions. The ring fixes the orientation of the heteroatom and in particular fixes the orientation of its lone pairs relative to the atoms around it. Heterocycles can be saturated as well as unsaturated. Examples of saturated heterocycles are tetrahydrofuran THF, Esridines, Pyrolysidine, etc. Tetrahydrofuran are well known solvents for organic reactions. Saturated heterocycles occur as components of natural products. For example, Esridine are found in mitomycin, anti-tumor agents from Streptomyces lavandulae, and thyrane 2-carboxylic acid is a plant product isolated from asparagus. Synthesis of pyrrolidine and pyrolysidine. Synthesis of pyrrolidine. The retrosynthetic analysis of pyrrolidine is shown here in figure. According to the disconnection approach, the compound can be synthesized from 1,4-dibromobutane and ammonia. The synthesis of pyrrolidine can be achieved in two simple steps as per the disconnection approach explained in the figure. In the step 1, the carbon bromine bond of the 1,4-dibromobutane is polar in nature, so the lone pair of ammonia can attack the carbon which is slightly positive. This leads to the formation of a bromide ion which removes the proton to give the 4-bromobutane 1-amine and HBr as shown. In the step 2, the compound so formed above, that is 4-bromobutane 1-amine, undergoes cyclization via an intramolecular nucleophilic displacement to give the compound 1. The amine group with the lone pair again attacks the second carbon atom with the bromo group attached to it with the loss of HBr leading to the cyclization. Synthesis of 2,2-dimethyl tetrahydrofuran. The design of the synthetic steps for 2,2-dimethyl tetrahydrofuran as represented by structure 5 can be explained by the disconnection approach. The retrosynthetic analysis of the given compound 5 shows that it can be synthesized from 4-bromobutane 1-ol. This is achieved by 1-bond CO disconnection. The disconnection leads to the formation of the two functional groups can then be cyclized to give the desired product. Synthesis. The synthesis of 2,2-dimethyl tetrahydrofuran can be achieved by intramolecular Williamson's ether synthesis. The synthesis is achieved in two steps. Firstly, sodium hydride, which is a strong base, abstracts the acidic proton of the hydroxyl group, forming an alkoxide ion, which is represented by the structure 7. In the subsequent step, the oxygen containing the negative charge attacks the carbon of the carbon chlorine bond, which acquires a partial positive charge leading to the cyclization of the compound 7 and elimination of metal halide leading to the formation of the desired product. Synthesis of pyrolysidine. Pyrolysidine, represented by the structure 9, is a heterocyclic organic compound and is the central chemical structures of a variety of alkaloids found in plants and are used in various traditional medicinal systems like Ayurveda. To understand the synthesis of this important compound, retrosynthetic analysis is very helpful. Applying the disconnection approach to the compound 9, we can see that the carbon adjacent to the nitrogen undergoes functional group interconversion to develop aldehyde group on both the ends. As can be seen, the first cleavage between the carbon nitrogen bond leads to the formation of the aldehydic group at one end, and the second subsequent step, the second cleavage, shows that the starting material can be a dialdehyde with amine group, which can lead to the formation of a heterocyclic ring compound. The synthesis of pyrolysidine involves the concept of reductive amination. Condensation of secondary amines with an aldehyde or a ketone gives an iminium salt, which on reduction with sodium borohydride cyanide gives a tertiary amine 9. The synthesis is carried out in 4 steps. In the step 1, the lone pair on amine group attacks the carbonyl carbon to form iminium salt as shown in the structure number 12. The iminium salt so formed is reduced with sodium borohydride cyanide to give secondary amine. This reduces the iminium ions selectively in presence of the carbonyl group. The lone pair of the secondary amine then attacks the carbonyl carbon to form the iminium salt represented by the structure 13. This salt so formed is reduced with sodium borohydride cyanide to give the tertiary amine 9, which is the desired product. Synthesis of Esridines and Oxidanes. Esridines are reactive substrates in the ring opening reactions with many nucleophiles due to their strain in the ring. Retrosynthetic analysis. Disconnection approach shows that Esridine 14 is formed by 1,2 amino alcohols number 15. The cleavage between the carbon and the nitrogen leads to the formation of a alcoholic group at position 2 with the amine. Synthesis. In the step 1, the hydroxy group of beta amino alcohol, as represented by the structure 15, is converted to a good leaving group. The compound 16 loses a proton in the presence of the base sodium hydroxide to give the intermediate 17. The lone pairs of amine in the structure 17 then attacks the alpha carbon, eliminating the leaving group, and finally formation of 2-phenyl esridine takes place. Synthesis of substituted oxidanes. Oxidanes are important industrial chemical and are starting materials for production of various important chemicals and household products in the industry. Applying the disconnection approach to oxidane, it shows the involvement of a reagent equivalent to the nucleophilic carbene, which is a sulfur halide, as shown here in the structure 20. This reacts with a ketone or an aldehyde to give oxidanes. The synthesis of oxidanes henceforth can be achieved by the following steps, starting from dimethyl sulfide as represented in the disconnection approach. The dimethyl sulfide on reaction with methyl iodide forms trimethyl sulfonium ion. The trimethyl sulfonium ion is converted to dimethyl sulfonium methylide in presence of a base. The dimethyl sulfonium methylide then reacts with the ketone by a net methylene transfer to form di-substituted oxidanes. Synthesis of oxazole and oxetane derivatives. Synthesis of ethyl 2R 3S 2-methyl hexahydropyrrolo 1,2-B isoxazole 3-carboxylate as represented by the structure 23. The retrosynthetic analysis of the given compound shows that it can be synthesized using nitrone represented by structure 24 and E-ethyl 2-enoate represented by the structure 25 in the given figure. The cleavage of the carbon-carbon bond and the carbon-oxygen bond leads to the formation of the two precursors, which can then be reformed in the synthetic approach to give the desired product. Looking at the synthesis of 2-ethyl 2R3S 2-methyl hexahydropyrrolo 1,2-B isoxazole 3-carboxylate is given in the figure and explained in the following 4 steps. In the first step, the N-ethyl pyrolysidine undergoes oxidation to give N-ethyl pyrolysidine N oxide. The so formed compound then on heating undergoes elimination to give pyrolysidine 1-ol. Pyrolysidine 1-ol undergoes oxidation to give nitrone. The cycloaddition of nitrone and E-ethyl but 2-enoate gives the desired product and the trans-stereochemistry of the unsaturated ester is preserved. Synthesis of 2-methoxy 3,3-dimethyl 2-phenyl oxetane. The disconnection approach shows that 2-methoxy 3,3-dimethyl 2-phenyl oxetane is synthesized from 3-hydroxy 2,2-dimethyl 1-phenyl propane 1-one, which on further disconnection shows that 2-methyl 1-phenyl propane 1-one and formaldehyde are the starting reactants for the desired product. The synthesis of the given compound can be achieved in the following 3 steps. In the step 1, 2-methyl 1-phenyl propane 1-one and formaldehyde undergoes Cannizzaro reaction to give the condensed product 1-hydroxy 2,2-dimethyl 1-phenyl propane 1-one. To make the conditions for cyclization favorable, the hydroxyl group in the given structure is converted into a better leaving group by reacting it with tosyl chloride in presence of pyridine. Methoxide ion attacks the carbonyl group, creating a negative charge on oxygen, which attacks the carbon containing the leaving group O tosyl. This leads to the cyclization and henceforth an easy formation of the given compound. To summarize, the heterocycles are the cyclic compounds that contain, apart from the carbon atoms, one or more heteroatoms like oxygen, nitrogen and sulfur. They can be saturated as well as unsaturated. The design and synthesis of pyrolysidine is explained using retrosynthetic analysis. The design of synthetic steps of 2,2-dimethyl tetrahydrofuran is explained by disconnection approach. The retrosynthetic analysis is used to explain the synthesis of pyrolysidine and their derivatives. The synthetic steps and retrosynthetic analysis of Esridine and oxidanes have been very well explained. The synthetic steps and the retrosynthetic analysis of oxazole and oxytanes are explained. Retrosynthetic analysis of ethyl 2R3S 2-methyl hexahydropyrrolo 1,2-B isoxazole 3-carboxylate shows that it can be synthesized using nitrone and E-ethyl but2-enoate with the desired stereochemistry.